Refractory degradation damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of refractory degradation based on API 571. Both thermal insulating and erosion-resistant refractories are susceptible to various forms of mechanical damage, cracking, spalling and erosion, as well as corrosion due to oxidation, sulfidation and other high-temperature mechanisms. Refractory degradation damage refers to the deterioration or decline in the structural integrity and performance of refractory materials, which are designed to withstand high temperatures and harsh environments. Refractories are commonly used in industrial applications such as furnaces, kilns, incinerators, and reactors, where they must endure extreme thermal, mechanical, and chemical stresses. Characteristics of refractory degradation includes: Number 1 is thermal shock. Rapid temperature changes can cause refractories to crack or spall. This is particularly common when cold materials are introduced into a hot environment, leading to differential expansion. Number 2 is chemical attack. Exposure to aggressive chemicals, such as slag, molten metal, or corrosive gases, can erode the surface of refractory materials. This degradation often results in reduced structural strength and thermal resistance. Number 3 is mechanical wear. Continuous mechanical stress from vibration, thermal cycling, or physical abrasion can lead to wear and tear, compromising the refractory's ability to retain heat and protect underlying structures. Number 4 is phase changes. Certain refractory materials may undergo phase transformations at high temperatures, altering their physical properties and potentially leading to instability in failure. Number 5 is moisture infiltration. Water or steam can penetrate refractory materials, especially those that are porous, leading to hydrothermal reactions that weaken the material over time. Consequences of refractory degradation includes: Number 1 is reduced performance. As refractories degrade, they lose their insulating properties, leading to increased energy consumption and heightened operational costs. Number 2 is unplanned downtime. Damage can result in the need for unexpected repairs or replacements, which can disrupt production schedules and incur significant financial losses. Number 3 is safety hazards. Compromised refractories can pose safety risks, such as the potential for explosions or the release of hazardous materials if thermal integrity is lost. Refractory degradation damage mechanisms affected materials based on API 571. Refractory materials include insulating ceramic fibers, castables, refractory brick and plastic refractories. Refractory degradation can affect various materials used in high-temperature applications, such as in furnaces, kilns, incinerators, and other industrial processes. The specific materials affected by refractory degradation include: Number 1 is refractory bricks. These are the primary materials used in lining furnaces and kilns. Degradation can manifest as spalling, cracking, or erosion due to thermal cycling, mechanical stress, or chemical attack. Number 2 is castables. These are heat-resistant concrete-like materials that can be poured into place. They can suffer from shrinkage, cracking, and erosion due to thermal and chemical exposure. Number 3 is monolithics. Similar to castables, these materials include a variety of non-brick refractories that can be applied as a dense or insulating layer. They can degrade through cracking or wear due to heat or abrasion. Number 4 is ceramics. High-temperature ceramics can also show signs of degradation through thermal shock, chemical attack, mechanical failure, or phase transformations. Number 5 is insulating refractories. These materials are designed to minimize heat loss and protect structural components. They can degrade due to high temperatures and mechanical loading, resulting in loss of insulation properties. Number 6 is fiber refractories. These are made from ceramic fibers and are used for insulation and to provide protective linings. They can degrade through thermal cycling, mechanical stress, and chemical exposure. Number 7 is mortars and binders. These materials hold refractory bricks and castables together. They can suffer from cracking, shrinkage, or chemical deterioration, leading to structural integrity loss. Number 8 is protective coatings, often applied to refractory materials to enhance durability. protective coatings can degrade due to high temperatures, corrosive environments, or mechanical impacts. Number 9 is metal components. Although not refractory materials themselves, metals used in conjunction with refractories, such as supports or containment structures, can be affected by the condition of the refractory lining. Corrosion and overheating can lead to failures in these components. Refractory degradation can result from a range of factors including thermal cycles, mechanical wear, chemical attack, from slag, ash, or gases, and erosion. Monitoring and managing these factors are crucial for maintaining the performance and longevity of refractory linings. Refractory degradation damage mechanisms. Critical factors based on API 571, refractory selection, design and installation are the keys to minimizing damage. Refractory lined equipment should be designed for erosion, thermal shock and thermal expansion. Dry-out schedules, cure times and application procedures should be in accordance with the manufacturer's specifications and the appropriate ASTM requirements. Anchor materials must be compatible with thermal coefficients of expansion of the base metal. Anchors must be resistant to oxidation in high-temperature surfaces. Anchors must be resistant to condensing sulfurous acids in heaters and flue gas environments. Refractory type and density must be selected to resist abrasion and erosion based on service requirements. Needles and other fillers must be compatible with the process environment composition and temperature. Refractory degradation can significantly impact the performance and longevity of refractory materials used in high-temperature applications, such as furnaces, kilns, and reactors. Key factors that contribute to refractory degradation include: Number 1 is temperature. Elevated temperatures can lead to thermal stress, which can cause phase changes, melting, or softening of the refractory materials. Understanding the maximum service temperature and the temperature gradients is critical. Number 2 is chemical environment. Exposure to corrosive chemicals, such as molten metals, slag, or acidic gases, can lead to chemical attack, resulting in erosion, spalling, or loss of structural integrity. Number 3 is mechanical stress. Mechanical forces, including thermal expansion and contraction, load-bearing stress, and vibration, can lead to cracking and spalling of the refractory material over time. Number 4 is moisture and gas penetration. The presence of moisture or reactive gases can cause hydration, oxidation, or other chemical reactions that degrade the properties of the refractory. Number 5 is physical properties. The inherent characteristics of the refractory materials, such as porosity, density, and thermal conductivity, play a crucial role in their resistance to degradation. High porosity can lead to increased susceptibility to chemical attack and thermal shock. Number 6 is thermal shock resistance. Rapid temperature fluctuations can induce thermal shock, causing cracks and failures in the refractory. The material's ability to withstand these changes is critical. Number 7 is service time. Prolonged exposure to extreme conditions can accumulate damage over time, leading to degradation failures. The life cycle of a refractory material is crucial in assessing its performance. Number 8 is installation quality. Improper installation can lead to issues such as cold spots, insufficient joints, or voids, all of which can significantly affect the long-term performance of refractories. Number 9 is refractory type. Different types of refractory materials, e.g., alumina, silica, zirconia, etc., exhibit different degradation behaviors based on their composition and properties. Selecting the right type for the specific application and exposure conditions is vital. Number 10 is operating conditions. Factors such as load cycling, operational practices, and maintenance routines can further influence the degradation and lifespan of the refractory materials. Number 11 is erosion and abrasion. In certain applications, mechanical wear from the movement of materials, e.g., in a furnace, can lead to the erosion of the refractory lining, thereby reducing its effectiveness. Number 12 is contaminants. Impurities in the materials being processed, as well as contaminants from the environment, can adversely impact the performance of refractories. Addressing these critical factors through careful material selection, design considerations, and operational practices can help mitigate refractory degradation and extend the lifespan of lining systems. Refractory degradation damage mechanisms affected units or equipment. Based on API 571, refractories are extensively used in FCC reactor regenerator vessels, piping, cyclones, slide valves and internals, in fluid cokers, in cold shell catalytic reforming reactors, and in waste heat boilers and thermal reactors in sulfur plants. Boiler fire boxes and stacks which also use refractory are affected. Refractory degradation damage can affect a variety of units and equipment in industrial processes, particularly in industries such as metallurgy, cement, petrochemicals, and power generation. The affected units or equipment typically include: Number 1 is furnaces. This includes blast furnaces, electric arc furnaces, and induction furnaces where refractory linings are critical for containing high temperatures and protecting the furnace structure. Number 2 is kilns. In cement manufacturing, kilns are lined with refractory materials. Degradation can lead to reduced thermal efficiency and structural integrity. Number 3 is boilers. Refractory materials are often used in high-temperature zones of boilers to protect underlying structures. Degradation can lead to heat loss and operational inefficiency. Number 4 is reformers. In gas-to-liquid processes, reformers utilize refractory linings, and degradation can impact catalyst performance and process efficiency. Number 5 is vessels. High-temperature process vessels, such as those used in petrochemical and chemical production, can experience refractory wear that affects operational reliability. Number 6 is chambers. High-temperature processing chambers, such as those found in heat treatment, can also suffer from refractory degradation, potentially affecting product quality. Number 7 is incinerators. The refractory linings in waste incinerators protect against high-temperature combustion conditions, and degradation can lead to emissions issues and structural hazards. Number 8 is cooling systems. In some systems, refractory materials may be involved in cooling towers or other heat exchange applications, with degradation affecting heat transfer efficiency. Number 9 is ladles and tundishes. In steelmaking, the ladles and tundishes lined with refractory materials can suffer from wear, impacting the casting process. Refractory degradation can result from factors such as thermal cycling, chemical attack, mechanical stress, and erosion. Regular inspections and maintenance are essential to mitigate these effects and ensure operational efficiency and safety. Appearance or morphology of refractory damage mechanisms. Based on API 571, refractory may show signs of excessive cracking, spalling or lift-off from the substrate, softening or general degradation from exposure to moisture. Coke deposits may develop behind refractory and promote cracking and deterioration. In erosive surfaces, refractory may be washed away or thinned, exposing the anchoring system. See Figure 4:59, damaged refractory in ferrules. Refractory degradation refers to the deterioration of materials that are resistant to heat, such as those used in high-temperature industrial applications, e.g., kilns, furnaces, reactors. The appearance or morphology of refractory degradation damage can vary depending on the type of degradation mechanisms at play. Here are some common appearances associated with different types of refractory degradation. Number 1 is cracking. Visible cracks can form in the refractory material. These cracks may be microcracks, small, barely visible, or larger fissures that penetrate deeply into the material. Cracking can result from thermal cycling, mechanical stress, or chemical attack. Number 2 is spalling. This is characterized by the flaking or chipping of the refractory surface. Spalling occurs due to rapid temperature changes, thermal shock, or the expansion and contraction of the material during heating and cooling cycles. The surface may appear pitted or uneven. Number 3 is erosion. Erosion can lead to material loss from the refractory surface, typically caused by the flow of gases, molten materials, or abrasive particulates. The affected areas may show signs of having been worn away, often creating a smooth or polished surface. Number 4 is fused or melting areas. in cases where the refractory has been subjected to extreme temperatures, localized melting or fusion may occur. These areas may appear glossy or glassy compared to the surrounding material, which may remain intact. Number 5 is color change. Changes in color can indicate chemical reactions occurring within the refractory material. For example, oxidation of certain components may lead to discoloration. Number 6 is corrosion. If the refractory material is exposed to corrosive environments, such as in the presence of acidic or basic substances, signs of corrosion may include surface roughness, irregular pitting, or color changes. The specific appearance of refractory degradation damage is influenced by factors such as the type of refractory material, the operating conditions, temperature, pressure, and chemical environment, and the duration of exposure. Regular inspection and maintenance are crucial to identifying and addressing these forms of degradation to prevent failure in high-temperature applications. Refractory degradation damage mechanisms prevention and mitigation based on API 571, proper selection of refractory, anchors and fillers and their proper design and installation are the keys to minimizing refractory damage. Refractory degradation refers to the deterioration of refractory materials, which are used to line high-temperature furnaces, kilns, reactors, and other industrial processes. This degradation can lead to energy losses, reduced efficiency, and potential safety hazards. Prevention and mitigation strategies for refractory degradation include: Number 1 is material selection, include. Number A of is material selection is choose the right refractory material, select materials that are specifically designed for the operational environment, considering temperature, chemical exposure, and mechanical stress. Number B of material selection is high-quality refractories. Invest in high-quality refractories that offer better resistance to wear, thermal shock, and chemical attack. Number 2 of prevention and mitigation strategies for refractory degradation design optimizations include. Number of design optimizations is proper design. Ensure that refractory linings are designed to accommodate thermal expansion and contraction to reduce stress and cracking. Number B of design optimizations is use of insulation. Properly insulate the refractory lining to minimize heat loss and maintain temperature stability, which reduces thermal cycling and cracking. Number 3 of prevention and mitigation strategies for refractory degradation is operating practices, include. Number A of operating practices is temperature control. Monitor and control the temperature to prevent excessive thermal gradients that can lead to thermal shock. Number B of operating practices is regular maintenance. Implement routine inspections and maintenance to identify early signs of degradation. This should include visual inspections and non-destructive testing methods. Number C of operating practices is minimize thermal cycles. Reduce the frequency and severity of startup and shutdown cycles to minimize thermal cycling. Number 4 of prevention and mitigation strategies for refractory degradation is chemical management, includes. Number A of chemical management is control chemical exposure. Monitor and control the exposure to corrosive materials or gases that may lead to chemical degradation of the refractory. Number B of chemical management is use of protective coatings. Apply protective coatings where appropriate to enhance chemical resistance and reduce wear. Number 5 of prevention and mitigation strategies for refractory degradation is mechanical protection, includes. Number A of mechanical protection is reinforcement. Use reinforced refractory linings, such as incorporating metal or ceramic fibers, to enhance mechanical integrity and resistance to cracking. Number B of mechanical protection is prevent erosion. Position and design equipment to minimize erosion from gas flow, particularly in high-velocity environments. Number 6 of prevention and mitigation strategies for refractory degradation is technological solutions, includes. Number A of technological solutions is use of sensors. Deploy sensors to continuously monitor the condition of refractories, including temperature and stress levels, allowing for proactive management. Number B of technological solutions is advanced diagnostics. Utilize advanced diagnostics, such as thermography and ultrasonic testing, to assess refractory conditions without requiring extensive shutdowns. Number 7 of prevention and mitigation strategies for refractory degradation is training and awareness, includes. Number A of training and awareness is educate personnel, train operators and maintenance personnel on best practices for handling, installing, and maintaining refractory materials. Number B of training and awareness is create awareness, raise awareness about the importance of refractories and the potential impact of degradation on operational efficiency and safety. Implementing these prevention and mitigation strategies can significantly extend the life of refractory materials and reduce the risks associated with their degradation. Inspection and monitoring for refractory degradation damage based on API 571, conduct visual inspection during shutdowns. Survey cold wall equipment onstream using IR to monitor for hot spots to help identify refractory damage. Refractory degradation is a critical issue in various industrial applications, particularly in high-temperature processes like those found in metallurgical, ceramic, and cement industries. Inspecting and monitoring refractory materials for degradation is essential to ensure the safety and efficiency of the operations. Here are several methods used to detect refractory degradation. Number 1 is visual inspection. Regular visual checks can help identify surface cracks, spalling, and discoloration. This method is often the first step in assessing the condition of refractory linings. Number 2 is thermography. Infrared thermography can detect temperature variations on the surface of the refractory. Hot spots may indicate areas of degradation or failure, allowing for targeted assessments. Number 3 is ultrasonic testing. UT ultrasonic waves can be used to detect internal flaws. By examining the reflection and transmission of ultrasonic waves through the refractory material, operators can identify cracks, voids, or other structural weaknesses. Number 4 is radiographic testing. RT X-rays or gamma rays can be employed to visualize internal structures. This method can provide images that reveal hidden cracks or density variations indicative of degradation. Number 5 is acoustic emission monitoring. AEM. This technique involves listening for high-frequency waves generated by crack propagation and other material changes. Continuous monitoring can provide real-time data on the health of the refractory. Number 6 is microscopy. Scanning electron microscopy, SEM, or optical microscopy can be used to examine the microstructure of the refractory material. This can provide insights into where mechanisms, chemical attack, and other degradation phenomena. Number 7 is chemical analysis. Analyzing where debris or the refractory material itself can identify chemical changes, such as oxidation or corrosion. Techniques such as X-ray fluorescence, XRF, or energy dispersive X-ray spectroscopy, EDX, can be used. Number 8 is mechanical testing. Performing routine mechanical tests like compressive strength, flexural strength, and abrasion resistance tests can help assess the performance of the refractory material over time. Number 9 is infrared, or IR, sensors. Embedding IR sensors in refractories can provide continuous monitoring of operating temperatures. Deviation from expected temperature profiles may indicate localized degradation. Number 10 is thermal cycling tests, subjecting refractory samples to simulated operational conditions to understand how material responds to thermal stresses and to identify early signs of degradation. Number 12 is finite element modeling, or FEM. Although not an inspection method in the conventional sense, FEM can predict the performance and identify potential failure points in the refractory based on operational parameters. Conclusion: effective inspection and monitoring of refractory materials involve a combination of these methods, tailored to the specific application and environmental conditions of the refractory system. Regular assessment and proactive maintenance can mitigate risks related to refractory degradation, enhancing safety and efficiency in high-temperature operations. Thank you.